Hi everyone, welcome to my YouTube channel. In today's video, we'll be discussing about the forwarding process in Cisco devices. And this is the continuation of the previous session from the chapter 1. So let's start the topic. And before we start, so if you guys like the video and would like to share it with your friends so that it will helpful for them, you can go ahead and subscribe, like the videos, and then share it with your friends. Let's discuss about the forwarding process in Cisco devices. IP packet forwarding, also known as IP packet switching, refers to the process where a device receives a packet on one interface, right, and decides whether it should be forwarded or it should be dropped, and how to forward it, right. That determines the appropriate outbound interface. So when we say term switching means when something is coming inside and coming to the router, right? It has to process and whether drop it or it has to send it out. So that's what we call it as in packet switching in the layman terms. So to efficiently handle high volume of packets, and Cisco developed fast switching and CEF. CEF is nothing but Cisco Express Forwarding Table. So using the CEFs, they form a table and that is used for forwarding all the traffic, or you can say switch the traffic, which optimize the packet forwarding process on routers. Let's see what is, there are different types of switching. So first let's discuss about the process switching. So Cisco routers traditionally, right, before CEF, okay, when they introduced the router, right? So those times, Cisco routers traditionally used process switching, also known as a software switching or slow path. Why we are saying slow path? Where the all the packets are handled in the CPU, so that causes delay in processing the packet, because each and every packet is sent to the CPU, and CPU has to process one by one. So that will lead to a small delay. So that's why it's called as a slow path. And this method is slower and consume more CPU resource, making it less efficient for high volume traffic. Therefore, router switches packets in hardware whenever possible to improve the performance. Because consider if there is like I have like 10 gig of link or 100 gig of link, right? So each and every time when you when you want to switch the traffic, and it has to go to the CPU, and it overload the CPU by default, right? When there is a more traffic. So that time what happens is whenever the hardware switching packet is possible, that it switch to the hardware switching. If suppose some packets are not able to handle, then it will go to the software switching. And there are conditions that we will discuss when the traffic is sent to the CPU, when the traffic is hardware switching in the coming slides. Next, when a router receives an IP packet, it decides whether to forward or drop it. That's what we discussed in the previous slide. Under process switching, router first strip the layer 2 header and check the destination IP address against the routing table. And if the match is found, it updates the next of MAC address before forwarding the packet out of the appropriate interface. By default, when we say the IP routing, right, switching, so it has to know the, so basically we need to understand whether it's forward based on layer 2 or based on layer 3. Here the packets if are, by default in, L3, its default and IP packet switching will be on the layer 3. So it has to open the IP packet and see what IP address, destination IP address there. So for that, you need to first remove the layer 2. Then you will have to look up the layer 3 address for the routing lookup. Then once it decide the destination, what it will do, again it will uh, change the destination MAC address here, because each and every hop the MAC address will be will be changed. So it has to change the next hop MAC address, then send the packet to the next router or next available device. So this is the small chart that I have put. Say when the packet arrives, so what it does is a process switching. So it will refer the routing, it will go to the CPU directly, then refer the routing table, then send the packet to the out. And Cisco uses fast switching and Cisco Express forwarding that I told you in the previous slide. is a Ceph. So what it does is it enhances the process switching for a large volume of packets. Process switching is now used as a fallback plan for Ceph. It processes punted IP packets when Ceph cannot switch them. For an example, by default, what it does is it all the packets when it comes, it will do the Ceph, right? There are some cases where it cannot, there is no destination lookup in the Ceph table. So that time it will default switch to the process switching, or if the Ceph is not available, there is some hardware issue, right? On the Ceph, it's not able to form. That time it will switch to the softer switching. So it's just acting as a fallback for now. The following packets are need to be handled by the software switching. Okay. So even if we have the Ceph, but by default in Cisco routers, there are conditions that the packets will be forwarded to the software switching, or the CPU will handle the packets. So let's see what are those packets. So packets originated or destined for the router using control plane or an IP routing protocol. Consider you have an IP protocol which is running. So when it sent, it originated from that router to another next of router, right? So that packets will be handled by the CPU or the software switching. And packets that are complicated for the hardware, such as IP packet with IP options, right? So those will be handled by the software switching in Cisco. And the last condition is packets that are needed further information which is not yet known, like our protocol. Consider a scenario where the ARP did not populate the MAC address for the IP for the destination. So the ARP is not properly populated. So then it will not be updated, right? So for those packets will be handled by the process switching. Even your ICMP packets destined to the router, that's handled by the CPU only. So any packet that is destined for the router, right? So that is handled by the CPU. So let's see how process switching work here. Consider this, example, the chart. Okay. Before I deep dive more into, let me explain few things. You can see that, right? There's a CPU will be there. Under the CPU, you have routing table, hop table is there, and Ceph will be separated. Okay. And now what happened is the hop table, right? Hop table used to map the IP address to the MAC address. So all my connected interface, right? And then next stop MAC address next stop IP MAC address will be populated in my ARP table. So once it is populated, what will happen is next it will send it to the Ceph. Okay. At the same time, you have protocols like static, connected, and OSPF, or any other protocol, BGP or AGRP, right? So it will form a routing table saying that whether it's a OSPF or it's a static or connected, and what is the prefix length, what is the outgoing interface. So those informations will be fed into the Ceph. Now Ceph as the routing information as there, it knows in outgoing interface what is the MAC address for that outgoing interface. Also it is aware. Also the destination address, right? Once it has everything, when the packet comes, then Ceph will switch it the egress packet. The same theory that I have put it. When the router receives an IP packet from the input interface, and the Ceph cannot switch the packet, right? So consider if the R table is not populated for some reason, right? Or populated, so that time what will happen is the packet will be punted when sent to the CPU. The routing table and R table are checked to identify the next hop address, right? I told you the routing table, the ARP table. Both are consulted and see what is the outgoing interface MAC address. It will then what happen once it has everything. So the once the IP packet comes, if it is routing table and ARP table for the outgoing interface MAC, what it will do? It will swap the MAC address, right? And then it will send the packet and it will change the IP TTL value and whatever the information that has to be changed in the IP packet. So that will be changed and then packet will be sent on the egress interface. And the routing table routing information stores the information directly connected protocols and the outgoing interface from the app. Now we discussed about how the process switching and stuff works. Let's see Cisco Express Forwarding. So Cisco Express Forwarding is a proprietary Cisco switching method and is default switching mechanism. On all Cisco platforms utilize the specialized hardware such as application-specific ASIC and network processing units. By leveraging these hardware components, CIF enables high throughput and efficient forwarding on hardware-based routers. Then we need to know about the TCAM. A switch ternary content address memory, that's the full abbreviation of TCAM. That's what it does is it enables the matching and evaluating packet based on multiple fields simultaneously. So that's used in the CIF in the hardware, right? So TCAM entries use the value, mask, and results VMO format. The values specify which packet to check. Let's consider it's an IP address or it has to check the protocol. So whether which bits, so that will be matched accordingly in the TCAM. Because TCAM operates in hardware, it provides much faster processing and greater scalability compared to the process switching. Let's see, there are two types of forwarding. Okay, let me explain. One is the centralized forwarding. When a route process engine is equipped with a forwarding engine so that it can make all the packet decision. This is also known as centralized forwarding architecture. For a centralized forwarding architecture, when a packet is received on the ingress card, right, it is transmitted to the forwarding engine on the route process. Then, as you can see, once the route process, what all the components it has, the route process has forwarding engine. Inside that, after that, within the forwarding engine, you have CIF also there, right? Then forwarding engine examines the packet header and determine that packet will be sent out of which egress ports, because forwarding engine has the own CIF, right? So based on that, it will decide, and then the packet will be sent out of the egress packet. If it is distributed, it come to switch fabric, then switch fabric will send it to the RP, route processing engine. Route processing engine will have the forwarding engine, which has the CIF. Then it check the table, CIF table. Then it decides which outgoing interface. So traffic will exit on the particular line card. Now next is distributed forwarding. Okay, the line cards equipped with forwarding engine. So now we are seeing that there is a separate route processing engine, right, and a forwarding engine inside. So consider there are like advanced line cards, right? So like advanced routers, they have CIF or the forwarding engine on the line card itself. So though that is known as a distributed forwarding engine. You have RP separately, but you have each line card will have the forwarding engine. So that you can see then like most of the advanced like routers in Juniper or Nokia. So that does this. For a distributed forwarding engine architecture, when a packet is received on the ingress line card, it is transmitted to the local forwarding engine. Okay, so here you can see there is route processing engine is separate, and each line card, ingress line card we have, egress line card I have, right? So when the traffic comes, right, the ingress line card itself, the destination address will be decided, okay, and then it will be switched via to the egress line card, right, via the switch fabric, and then the traffic will be sent out. So in this case, it will bypass the route processing engine. So mostly this type of scenario distributed forwarding, right? So it will be in the advanced routers or higher end routers. Okay, we discussed about CIF, right? In CIF itself, also we discussed about the software switching. Now in CIF itself, there are two types are there. One is the software Ceph, and next one is the hardware Ceph. So first let's discuss about the software Ceph. The software Ceph is also known as software forwarding information basis that consists of the following components. There are two components we have. One is the fib and next one is the adjacency table. Fib is nothing but your forwarding information base. The fib is directly derived from the routing table and it holds the next hop IP address for each network and destinations. And also it mirrors the forwarding details of IP routing table. And also whenever there is a change in the routing table, so there is a OSPF flaps or the any changes in the interface, right? So this will get reflected. Whatever the changes in the rib, so that's what we call it as fib and rib. Rib is the routing engine base and is the forwarding engine base. So whatever that output is here is derived from the rib only. So that's when you see the show IP route, so you can see like maybe 2 or 3 routes in the in the rib, but only one is based on the best route that will be installed in the fib. So fib is more important for switching the traffic. So next is adjacency table, right? We discussed about the fib. Next is adjacency table. Why do we need an adjacency table, right? So adjacency table, so it stores all the directly connected interfaces. Consider in the router, you have like 4 or 5, 1, 2, 3, 4, 5 interfaces are there, right? So it has all the ARP, the next hop, what is the next hop, and what is the IP address of the what is the MAC address. So that will be derived in the show IP ARP, right? So this output, whatever the ARP has, right, that will be copied to the adjacency table. So that helps to map the MAC address for the egress interface. Basically, whatever the ARP, so like how rib is copied in fib, the IP ARP, right? ARP table will be copied to the adjacency table. Is simple. Just you have to remember that. Okay. Consider this output or the how. Let's discuss how software Ceph works. We discuss about software switching and Ceph, and let's see how software Ceph works. And upon receiving an IP packet, fib is checked for a valid entry, right? Once I am receiving an ingress packet here, okay, and then now what it has to do in the Ceph, right? In the in the Ceph itself, there are two tables. One is fib, which is copied from the routing table. One is adjacent. Next is adjacent table that is copied from the op table. So this is how the data details are copied from routing and op table. Next, the valid fib entries continue processing by checking the adjacency table for each packet's destination address. So here what we discuss about the software switching, right? So this is a Ceph. What we're discussing about is a Ceph, but you remember I like when we discuss about the software switching, it's not a Ceph switching, it's a software switching, right? So when the fib validates, and then it validates on the adjacency table for the MAC address. In case if the MAC address is not available, then the packet will be sent to the CPU to process it because it doesn't have the valid entry. That's where the software switching kicks in. But in case if there is a fib entry and there is a valid adjacency entry, then what happen? It will form the packet and then it will send to the egress interface. And this is what discussed when the software Ceph cannot handle a packet, right? The Ceph is pointed to the next lowest switching path, which is usually the process switching, the software switching, right? That is processed by the router CPU. And common reasons are there. The Ceph cannot handle packets, which we discussed, right? And one is like maybe there are packets that are carrying some features like IP protocol, IP options, right? That is not available. Then it will be forwarded to the CPU. In case if there is an ARP, so destination IP is there, but the next of MAC address is not there for the corresponding MAC IP, then it won't be able to process it. So that time it will be sent to the CPU to handle it. Then CPU decides whether to how to send it or it will drop it. That will be in the hands of CPU. Next is hardware Ceph. So hardware Ceph is the implementation of Cisco Express Forwarding using dedicated hardware. So whatever we discussed in the previous chapters are software Ceph, right? So whatever it is, it's all handled by the Ceph, in the software only, not in the hardware. So now we have one more method called hardware Ceph. So we have a special, um, hardware that will handle the Ceph, right? That's what we call it as a hardware Ceph. So obviously, right, when compared to software, hardware will provide the high performance switching at a line rate. And how hardware Ceph works? It's same like the software Ceph. Like the difference is it works on software, it works on hardware. So fib and adjacency table are built in the control plane that we are aware, right? Are downloaded into the hardware ASIC. Earlier, it will be there in the part of the software Ceph. In this case, now it will download it to the hardware itself. So when the packet arrives, the ASIC performs a fib lookup to determine the next hop IP address based on the destination prefix. The ASIC retrieves, as we mentioned earlier, for software Ceph for process switching. So they retrieves the adjacency information. That's the next of MAC and the egress interface from the adjacency table. And then obviously it has to rewrite the L2 forward whenever there is a packet switching is happening. So, and this will rewrite the L2 header without the intervention of CPU. And then the packet will be switched. And let's see what are the advantages of hardware Ceph. Hardware Ceph is very high speed forwarding at line rate, and it minimizes CPU load using CPU only control plain text. Consider if you're sending all the, like, consider you have a laptop, right? In your CPU is keep on, like you're using your CPU keep on, then what will happen, right? Your CPU will spike and it won't be able to, uh, you know, use the next application because CPU is already busy. So when you keep your CPU busy, then next process will have to wait. So in case of hardware switching, it doesn't happen because it's handled by the special hardware and it won't even pass it to the CPU. And it supports scalability in large enterprise and service provider networks, especially. That's what I said. This hardware stuff and all, right? It's all like it's like high-end devices, where this will be mostly used in the where you have like a number of like you have like high number of traffics, mostly in the service provider environment, and uses hardware resources efficiently for determining the forwarding performance. And next, will discuss about the stateful switchover, right? So this is one of the very good feature. It's there in most of the service provider, service vendors whenever they have the route processor, the dual route processing engine, or you can routing engine in Juniper, right? So see, like you have a route processor, right? RP. So that is actually maintains the all the network topology, learning the IP address, MAC address, all the protocols, and it builds the RIB also, right? You have the CPU, basically two CPUs that they call the route processor. So like you can PC Intel, I'm using Lenovo laptop, so I have the Intel CPU. So like that, there'll be two CPUs will be there in this, in the higher end hardware devices. So if one fails, the other should kick in. So that's how do we do it? That's what it's called a stateful switchover in layman terms. So consider there are two route processor are there, okay? And a route processor failure can cause routing protocol adjacency to reset and leading to packet loss and network instability. To avoid this disruption, it's often preferred to conceal the failure. So basically, we need to conceal it, right? Otherwise, what will happen when you have protocol adjacency? Will all the like, can I have 10 routers are connected? All the protocols will be flapped. Then all the traffics which is sent via that particular interface will get flapped, right? And there will be a actual data packet loss will occur. So we need to conceal that failure. and allow the routers to continue forwarding packets using existing Ceph entries instead of dropping the packets during the switchover. So when there is a failure, use the existing routing table, existing Ceph, and existing outgoing interface, right? So that how is done from one route process failure, it has to copy to the other RP. So the stateful switchover is a Cisco high availability features. That's what we call a high availability. Means even if your one is failed, the other will kick in and then it will start taking the process. Whatever that the person A is doing, the person will be B will be doing the same thing. So this high availability feature that allows a router or switch to continue forwarding packets without dropping any protocol session during a supervisor or route processor switchover. Let's see how this stateful switchover works. Device with dual supervisor engines or the route processor, we can say CPU also in a layman terms. Run in redundant mode, right? You need to make sure when you have dual RP, so you make it run in a redundant mode. So there are one is active, one is passive. So the active supervisors handle all the control plane and data plane tasks. So it's like you have OSPF neighbor is there, BGP session is going on, BGP neighbor. So BGP control packets is coming. So it's all handled by the active supervisor. And if there is any packet pointer to the route process CPU, so that is also handled by the active supervisor only. And now the standby supervisor is there, right? So what it does is it maintains a synchronized copy of the active supervisor. Let's say operational state. So what say active supervisor will have like 10 interface up. So that 10 interface will be status will be copied to the backup or standby supervisor. And it's an like active standby. So one is active and by standby. So when the active fails, the standby will kick in. So for that, all the information on the one CPU will be copied to the other CPU. So one active supervisor, right? That all the informations that has to bring the network up without any issues, right? Without any network instability. Whatever the information is required, even the ARP, even the interface, even the L3 routing table, even the protocol sessions, right? All will be maintained in the standby supervisor. So once the active supervisor fails, the standby supervisor immediately takes over with the same state information. That's why I told you it will even maintain the ARP, also the protocol states and everything that will be run on the standby. So if the standby primary fails, the standby will kick in and take over. And during the switchover, the interfaces will not flap. And the routing and the switching, right? The packet when it comes and going, or the any data packet which is coming during the failure of the RP, so that will still in the forwarding state. So next concept that we will discuss about the SDM template switching database manager. SDM, the abbreviation is Switch Database Manager. So why do we need this SDM template? So SDM templates allow you to optimize how a Cisco switch allocates hardware resource, right? So we already discussed about the TCAM, right? So hardware, right? So TCAM also the memory to different support features based on the role of a switch in the network. So what is the purpose of it? Switches basically any hardware device, right? So when you go to hardware, right? So there will be anyway limited resource will be allocated because you need to allocate for routing, you need to allocate for security, QoS entries, and you have a number of VLANs. So everything will be will be maintained, right? You will not have like n number of resource will be allocated or available to do all this. So when you have different network environment, require different resource allocations, right? Consider you have a campus 8 switches, right? That need more VLAN and MAC address to be supported because you are in college, some campus. And consider you have in distribution switches, like which is higher than the access layer, right? That may need more routing and ACL resources. You need to have like L3 capability, also the access control list resource will be there. Consider you are in the access layer switch, right? So with wipe you will have the data, also the call is going. So for those you need more VLAN as well as the QoS entries will be there. So they using the SDM templates, you can optimize the switch to support your specific deployment requirements. Let's see how to view the SDM templates. So this is the command show SDM prefer will show you the output. So you can, modify it, optimize it. So that's all for the chapter 1, session 2. And let's discuss what are the key topics that we discussed. So we discussed about the collision domains, VLAN, and what is access port, trunk port, how to configure access port, trunk port, and we discussed about the CAM, ARP, IP routing, right? How the IP routing happens, and what is IP routing, and what is especially CEF, what is TCAM table, and in CEF itself there are two types, right? When like software CEF, hardware CEF. At last, we discussed about how to do the network up and running when your RP failure or your CPU failure, right? And then finally, we discuss how do we optimize everything. Not everything. How do we optimize the resource using the SDM template, the switch. And the final one, this is a task and this is a command and syntax for it, right? This I'll try to copy paste it in my chat in the description and see that if I'm able to paste it, and then I'll give it to you guys so that it will helpful for you guys to practice it. So you can see like how do we do a VLAN configuration, access port configuration, trunk port configurations, and static MAC address entry, and how do we modify the SDM database which we discussed, right? So secure device manager database, how do we do it, and also the configuration plus what are the commands that we can use to execute and show the outputs, see the outputs, right? So this is the command syntax that we have. So this also I'll give it in the description so that when you do a lab practice, it will be helpful for you guys to analyze it. Hope you guys like this video, and if you like it, hit a like button for sure because it will reach to more peoples who just wanted to learn from our YouTube channel, from my YouTube channel, so they can learn it. So you guys have to do me a favor of hitting a like button, subscribe, and share it with your friends. You think that it may helpful for them. And thank you very much for watching. We'll see you in the next video.